Doug Arnold continues with the...
Okay, so let me point out where we are and more importantly where we're going. So last time it was just sort of prereqs. We talked about chain complexes and we talked about closed unbounded operators on Hilbert spaces, and the merger of those two items gave us Hilbert complexes. And I'll quickly review the definition in a second. There were no PDEs there. Well, of course, there's no PDEs because I was doing this in the abstract. We're talking about an abstract Hilbert space, but there are no problems to solve. I didn't have equations. So obviously, we want to get to something that's going to represent a PDE, and that's going to be the main topic of today, at least the first half of today. For every one of these chain complexes, in every space in the chain complex, in the Hilbert complex, there is a operator equation which is going to represent an important PDE. And our main example of a Hilbert complex was the de Rham complex. Here I've written the 3D version of it using scalar fields and vector fields. And so at each of these places we're going to have certain PDEs that are going to involve the operators, so they're going to involve divs and curls and grads and things like that. And these are going to be important PDEs that we're going to be interested in solving. So that's the abstract Hodge-Laplacian we'll talk about today. And now I haven't gotten to discretization, which is what this whole business is about. So I hope today we'll get started on discretization of Hilbert complexes in that abstract framework of Hilbert complexes. And then we'll want to get to real complexes like this one here. In that case, then we'll have to talk about what are the numerical methods from the abstract framework. How do we make them and meet those hypotheses and make those work for a real problem that leads us to creating finite element differential forms. And then finally in the last lecture, which I may not get to, but if I get to, we'll get away from this complex and talk about other complexes and other PDEs. Okay? So here's a quick review of last lecture. There's a Hilbert complex. It consists of a sequence of Hilbert spaces W0, W1, blah, blah, blah. And between two consecutive ones, there's an operator, which we number as D's. Usually I won't write the superscript, just D. And these are unbounded operators, so they have domains, which I write as V. One thing you can do whenever you have a Hilbert complex is you can take the dual complex and you get operators going back the other way that I call D star, and they have domains too that are called V star. Another thing you can do whenever you have a Hilbert complex is you can talk about the harmonic forms, which are the things, they can write them in different ways. You can say the things in the null space of D, which are orthogonal to the range of D of the previous D, or you could also do that using duality, say they're the things in the null space of D and simultaneously in the null space of D star. So you start in the space, and if you go right or you go left, you get 0. Those are the harmonic forms. That's a finite dimensional space that's equal to in dimension to the cohomology. And then you get the Hodge decomposition, which says you can take your Hilbert space and break it up into the range of the D's, that's B, plus the range of the D stars, that's B star, plus the harmonic forms, that's an orthogonal decomposition. That puts all the null spaces and the ranges in clear relief. Here's the range of the two operators. The null space of D is just B plus the harmonic forms. The null space of B star is just B star plus the harmonic forms, and you can read off the orthogonal complements from that decomposition. And then the last thing we got is Poincaré's inequality, which is something quantitative. Given anything in one of the spaces that's orthogonal to the null space of D, it's bounded below by dz bounds above z. We have this Poincaré inequality. Okay, now how do we get a problem out of this that we want to solve? What is this good for when we're interested in partial differential equations as opposed to topology? So I don't need the whole Hilbert complex. I need 3 spaces in a row. So let's just take what we need and not write the whole thing. So there's a little piece of the Hilbert complex. 3 Hilbert spaces, 2 closed unbounded operators, and the null space, the range of the first contained in the null space of the second. So the first thing I can do is I can take the adjoint complex. So I put the adjoint arrows going back. Then what I can do is, if I'm in this middle space WK, I have an operator that maps that space to itself, namely I go right and I go back left by D star. I get a map from WK to WK. I could also go left and then right, D star or D star D. And if I add those two operators, that's the Hodge-Laplacian for this little Hilbert complex. D star plus D star D is a mapping from WK to WK called the abstract Hodge-Laplacian. If I did it on the de Rham complex, it would be called the Hodge-Laplacian. It's a closed, unbounded operator. What's its domain? Well, its domain is what it has to be. Everything in the domain of D. So when you hit it with D, it ends up in the domain of D star, and the opposite has to hold. So the domain is everything in the domain of D and the domain of D star, such that D of it's in the domain of D star and D star of it's in the domain of D. Now we get an interesting fact. Its null space is precisely the harmonic forms. That's why they're called harmonic forms. They're the null space of the Laplacian. How do you see that? Well, obviously anything that's in harmonic forms, that means it's in the null space of D, and D star is in the null space of L. But how about the other way? Well, if you have L u equals 0, that means d star u plus d star du equals 0 in our Hilbert space. Then let's take the inner product of that in our Hilbert space with u. Then from the definition of the adjoint, this d can go over to u.
D star.
Yeah, I'm missing a d, right? D star plus d star d. Thank you. So I take this d and I put it as an adjoint on d star, and I get d star squared, d star u squared. And I take this d star and I take its adjoint and put it on u, and I get u squared. And this is all allowable because u is in this domain, so the adjoints apply. So if L of u is equal to 0, d star u and du is equal to 0. So we have if and only if. The harmonic forms are exactly the null space of L. Also, you get that the harmonic forms are orthogonal to the range of L for a very similar argument. If you take L of u against a harmonic form H, and you do the same calculation, then when you bring the D over to the H, it kills it because H is in the null space of D star and it's in the null space of D. So this would equal 0 in that case. Okay, so why am I making a fuss about that? Well, now the problem we're going to want to solve is Laplacian u is equal to f, Lu equals f, and we're seeing here there's no chance that that's a well-posed problem if there are harmonic forms. Harmonic forms are in the kernel. So the harmonic forms measure to what extent the solution is not uniquely determined. Just like if you're trying to solve Laplace u, the scalar Laplacian u is equal to f, and du dn equals 0 on the boundary, the solution is only determined up to constant functions. For that problem, the constant functions would be the harmonic forms. On the other hand, just as for that problem, you have a Fredholm alternative, you can't solve the problem for arbitrary f because f has to be in the range of L, so f has to be orthogonal to the harmonic forms. Just like you can't solve a Neumann problem unless the right-hand side is orthogonal to the constants. Okay, so there's a problem we want to solve. Given an f, we want to find a u in the domain of the Laplacian, so Lu equals f. Well, that's not possible, Lu equals f, so we're forced to subtract off the component of f in the harmonic forms that we can hit in the range of L, and what's left over. This is subtracting the right constant from your right-hand side to solve a Neumann problem. And to make it unique, we want u to be orthogonal to harmonic forms. By the way, remember, very often you're solving a problem, there are no harmonic forms. If your domain has no holes in it, there are no harmonic forms, then you don't have to worry about all this harmonic form stuff. And then it's just Lu equals f. Okay, so to solve that, we're going to put it in some sort of weak formulation. That is, we're going to take the inner product with test functions. And there are two different natural ways to do this. The primal weak formulation is you look for, well, what you do is you multiply the equation by a test function v, and you use duality to move the operators over. You use the adjoint relationships. So this becomes the inner product of du with dv plus the inner product of d star u with d star v is the inner product of f minus phf with v. And this makes sense for u that's in v intersect v star and v in v intersect v star. And we take care of the non-uniqueness by making sure everything's orthogonal to the harmonic forms. So that's very natural, very simple. It's a whole lot like when you write minus Laplace u equals f, multiplied by test function v, get integral grad u grad v equals integral of fv. Turns out this is not the way to go. There's big problems with it, as we will see. There's another formulation. By the way, when I say it's not the way to go, it's not the way to go for discretization. It's perfectly fine on the continuous level. The other formulation is the mixed weak formulation. It looks a lot more complicated. For that one, we introduce a new variable. And what is this new variable, sigma? It's d star u. And the very first equation we write, so it's not in it's not in wk or vk, it's in vk minus 1. That's the statement that d star u should be in the domain of the previous d. Okay, so the first equation, what does it say? The inner product of sigma and tau is the inner product of u with d tau for tau in the domain of the previous d, dk minus 1. That's another way of saying sigma is d star u. So I'll write it down here so we don't forget. So what we've really, and then we have another equation that d of sigma plus, that's d of d star u. Now I need d star du equals f minus the harmonic forms. So that's what we're doing. We're breaking this equation, the Hodge-Laplacian, down into two equations, which are those two equations. So here's the second equation, d of sigma times a test function, and then the d star du, I use the adjoint relation to move the d over. And this is the harmonic form part. Don't worry about the harmonic form yet at the moment. So we have those two equations. And let's look at those equations. We're looking for then a sigma in one space, the vk minus 1 space, and a u in the vk space, only in the domain of d, not in the domain of d star. No d stars show up in this formulation, right? Everything is done in the domain of d. A little bit like when you're solving the scalar Laplacian, div grad u equals f, the numerical method you have has grads in it, but it doesn't use divs in it. It's integral grad u, grad v. Okay, and then if there are harmonic forms, we have to take care of them. So this is just a statement u is orthogonal to the harmonic forms. And this p is nothing other than the projection of f under the harmonic forms. Because if you take v as a harmonic form, these two terms drop out. Okay. Now, you're probably used to, when you deal with strong form and weak form of PDEs, a very common statement is anything that satisfies the strong form satisfies the weak form, and anything that satisfies the weak form, if it's smooth enough, satisfies the strong form. That's not the case here. Here, these are completely equivalent. Anything that satisfies the strong form satisfies the weak form, and anything that satisfies the weak form satisfies the strong form. And you might say, which weak form? Either one. They're all three are equivalent. So there's complete equivalence of these three forms in the following sense. Take any f in the Hilbert space WK, the L2-like space. Then the u you get by solving the strong form also solves the primal weak form, and vice versa. If u satisfies the primal weak form, then it is automatically in the domain of the Laplacian and satisfies the strong form. And in this case, if we set sigma to be d star u and p to be the harmonic component of u, then the triple sigma up satisfies the weak form. And finally, if you have a triple sigma up that satisfies the weak form, then u satisfies the strong form, and so the primal form. So these are completely equivalent. You could, at the continuous level, you can use whichever you want. And as I say, we'll find in the discrete level, it's best to use the mixed form. Then finally, sticking at the continuous level, because that's where we are now, there comes the question, okay, they're equivalent, are they well posed? If one is well posed, they're all well posed, are they well posed? And the answer is yes. So the situation is you give me any closed Hilbert complex, then you have a Hodge-Laplace problem, and it's always perfectly well posed up to the harmonic forms and can be written in three ways. This is the well-posedness statement. Well-posedness means for all f, there's a unique solution that takes into account harmonic forms, and the unique solution is bounded by f, and that's quantitative, and the constant is only depends on the Poincare constant. So that's the key number that measures well-posedness. And let me give you a hint how you prove this. So we're trying to show that one of these is well-posed. Well, actually, the easy proof would use the primal form. But I'm not going to use the primal form because when we go discrete, we're going to use the mixed form, and we won't have the option of using the primal form. So I'm going to show you that this mixed formulation is well-posed. So how do you do that? Well, those of you who know the Im-Sup condition know you use the Im-Sup condition, which means that you pick an arbitrary sigma u p, and then you have to show that you can come up with test functions tau vq such that this stuff on the right-hand side bounds the norms of sigma u p. That's sort of the Im-Sup condition. For all sigma u p, there exists a tau vq and an inequality. So here's the stuff on the right-hand side. I just add the equations together, cleverly choosing signs so it ends up to be symmetric. That's convenient. And what I have to do is that for any sigma up in the domain of vk minus 1, the domain of vk, and the harmonic forms, there exists a tau vq in the same place, such that that bilinear form coerces the norms. And I'm going to prove that's true where the constant only depends on the Poincare inequality. Let me not go through the whole details, but give you the key idea. So how are we going to control? We have to control sigma in the W norm, d sigma in the W norm, that's sigma in the V norm, u in the next W norm, du in the W norm, and p in the W norm. dp, of course, is 0. So we look up here and say, okay, how can I pick tau so I can get some control over sigma in W? Well, that's pretty obvious. I'll choose tau is equal to sigma, and I'll get sigma in W squared here. So I can control sigma in W. How can I control d sigma? Well, I look here. It's sitting over here. I just choose the test function v is d sigma, or minus d sigma, and I get the norm of d sigma squared. How can I get control over u? Well, let's hold off on that. This is the best term for getting control over u, but this can only get control of the piece of u that's in the range of d. There's also a piece of u orthogonal to the range of d that this doesn't see. So we'll have to somehow get that from the other terms. So let's hold off on that. How do I get control over du? Well, that's for free. I take v as minus u. How do I get control over p? That's easy. I take v is equal to p. So, and then I add them together with the right coefficients, and I would get my solution. And the only challenge is to get control over all of u, not just the part that's in the range of d. And for that we use the Hodge decomposition that says, well, u breaks into an orthogonal sum of 3 parts, a part in the range of d, a part in the harmonic forms, and a part orthogonal to the range of d. Sorry, a part orthogonal to the null space of d, orthogonal to both of these. So there's no trouble getting control over ub, because we have this u dt term. There's no trouble getting control over uh, because I take q here to be the harmonic part of u. Remember, q is a harmonic form here, so I have to take it to be a harmonic function, so I take it the harmonic part of u. The trouble is getting control over ub star, the part that's in orthogonal to the null space of d. And then we remember the Poincare inequality that says if you're orthogonal null space of d, you're controlled by du. And that's basically the proof. Okay, this slide is too busy, and let's just start from the red here and skip the top of it. So where do we stand? We stand that you give me any Hilbert complex, I have a Hodge-Laplace problem, and it's well posed. Is there anything else I can solve with this Hilbert complex? Well, just applying the Hodge decomposition, I get 2 more problems. So it's easy to check, and that's what the top of the slide is doing, that if you put your f, the right-hand side, happens to be in the range of d, then U, the solution U, is automatically in the range of D, which means the Hodge Laplacian reduces to a simpler problem. dd star U, the d star d term drops out in that case, and dd star U is equal to F, and du is equal to 0, and U is orthogonal mononic forms. This is it. U is in the range of D. So that means we have another problem we can solve. We can solve dd star U equals F. Those are the kind of problems that you see, like curl U equals F, divergence U is equal to 0. That's an important problem in electromagnetics. Of course, it can only be solved when F is in the range of the curl in that case. And there's an analogous thing with the B star problem that would be, in that curl case, that would be a grad div problem. So that gives us a new set of problems, an additional set of problems we can solve at each level of the Hodge, the Hilbert complex. So let's do some concrete examples. So I'm going to use this Hilbert complex, and I have to take 3 spaces in a row. I'll start with the simple cases where one of the spaces is 0. So at the left end, it's 0, L2 scalars go to L2 vectors by the gradient. And then, well, in that case, if you go back and look at the mixed form, there's no d star U to worry about because d star goes off to 0. So we only get the du dv term, and the only terms that show up here are again du dv. So actually these two formulations are the same. So you should always use the bottom formulation, but in this case it's the same as the top formulation. So that's just the usual stuff, grad U, grad V equals F. So that's the standard Poisson, the standard weak formulation of the Poisson problem with, in this case, Neumann boundary conditions. And we've taken care of the constants because those are the harmonic forms. That's why P is in R. We could also define a slightly different complex where the domain of the gradient was H01. And we did that, then we would get the usual Poisson equation for the Dirichlet problem. Okay, so nothing new at all here when we take the leftmost end of the Hilbert complex. Let's go to the rightmost end, from here to here. Vector fields go by divergence to scalar fields go to 0. In that case, the mixed formulation involves both variables, sigma in H div and U in L2. And so our method is find sigma in H div, U in L2, such that the inner product of sigma and tau minus the inner product of U and div tau is 0. For all tau in H div, the inner product of div sigma with V is equal to the integral of FV. And there are no harmonic forms on the right-hand side. This is the absolutely standard mixed formulation of the Laplacian, the equation number 1, when you study mixed methods for finite elements. And so that's what we get out of the Hilbert complex framework in this case. We get another way to solve the Laplacian that's very different than the standard way using grad-grad. And then there are the cases in the middle. So using either L2 vectors with grad and curl, or vectors, scalars with curl and div. So let's write down the adjoints. There they are. So if we take the grad and the div case, and we do it, I just write down the strong form, you get minus grad div plus curl. That's the vector Laplacian or Hodge Laplacian, rises in a lot of applications. And you get boundary conditions from the fact that the solution has to lie in the domain of D star, which is H0 div, which means the normal component has to vanish. And D of the solution, the curl, has to be an H0 curl, which means its tangential components have to vanish, so-called magnetic boundary conditions. And so this is a way to solve this second order PDE, system of PDEs, using the mixed formulation would introduce a new variable minus div U. And again, I will show to you why it's much better to solve this problem using an extra variable than it would be to solve it in this form here, in the primal weak formulation. And finally, what happens if you use the last three spaces, non-zero spaces? Then the operator turns out to be curl curl minus grad div. So it's actually the same operator. You get different boundary conditions. You get electric boundary conditions out of this thing. And the homology groups are the one forms for the Betty 1, has dimension of Betty 1, the tunnels through the domain for the first case, and the voids in the domain for the second case. And then these are well-posed problems.
Do you get the boundary conditions?
So you get the boundary conditions if you have this complex by the statement that the solution, you get the boundary conditions naturally, not essentially. You look at an equation like this. So let's try to interpret this equation. This equation holds if U is in the domain of D star and sigma is D star U. So let's now go back to the example and see what that means. So let's say in this one, U is a two form and it has to be in the domain of this D star. That means it has to be in the domain of the curl H0 curl, because the adjoint of curl with domain H curl is curl with adjoint domain H0 curl. So U, which was sitting over here, had to be in the domain of this operator, and that means U has to satisfy U cross N equals 0. Okay? So in this formulation where I start with this Hilbert complex, there are no boundary conditions that I built into the spaces. That was my choice. That means there are no essential boundary conditions. I didn't build them into the space. They come out naturally. Just like the Neumann boundary conditions for the scalar Laplacian come naturally. Okay? So that's the abstract Hodge Laplacian and what you get out of it for the Durham complex in 3D. You also get the DD star and the D star D problems, so you get various ways to solve curl-curl problems and grad div problems. But that's not all you can do with a Hilbert complex. So if you take a Hilbert complex, you get the Hodge Laplacian and the B and B star problems, but you can also get eigenvalue problems, time-dependent problems, and so forth. So here's the eigenvalue problem. So it's the eigenvalue problem for the Hodge Laplacian. D star plus D star du is some eigenvalue lambda times u. And that has a weak formulation, a weak mixed formulation, which I've written here. We don't have to worry about harmonic forms because they're just the eigenvalue of 0. So the harmonic forms are exactly the 0 eigenspace for this problem. In fact, that's one way to compute the harmonic forms. And we can use this, and this is the correct way, in my opinion, to find the eigenvalues of this operator. And this includes the eigenvalues of the curl-curl problem, which is the famous Maxwell eigenvalues, and eigenvalues of the grad div problems, and so forth. Here's another thing you can do. You can solve an evolution equation, what I call the Hodge heat equation, which is U dot plus the Hodge Laplacian of U is equal to F. Again, you don't have to take care of harmonic forms. They take care of themselves. Whatever present in the initial conditions just hangs around. And all you do is add in the weak formulation, that term U dot V. And I claim that this problem is always well posed too. So you give me any Hilbert complex, this is a well posed evolution problem. How do you prove that? Well, the way that we would prove that is to analyze an evolution problem, you basically have to analyze the stationary part and use the Hilly-Yosida theorem. And the previous statements that the problem is well posed for the Hodge Laplacian then implies the well postedness of this. You can also do the wave equation. This is probably one of the most interesting ones for applications. So the problem is what you would think it is. U double dot is equal to the Hodge Laplacian of U, or plus the Hodge Laplacian of U is equal to 0. You have to give two initial conditions. This comes out a little different. You might have thought that I put a U double dot here, but that's not what I do. And I introduce a new variable here, rho, which you didn't see before. So let me try to explain this. So as before, we introduced as a new variable D star U. I'm now also going to introduce a variable du called rho. I could have done that before. There were plenty of du's in my equations. I could have named them rho and had one more equation, rho equals du. Here it's important to do that. There it didn't add anything. And now, the approach I like, and we were discussing this at the poster session, there's different ways to turn the wave equation into a system with only first order and time. The way I like to do it is introduce as a new variable the time derivative, the velocity, so little u is capital U dot, as well as these two variables here. And then my system takes this form here. Where does this coming from? Well, since sigma is d star u, that means sigma dot is d star u dot, and u dot is little u. So sigma dot minus d star little u is equal to 0. The bottom equation is very similar. Rho is du, so rho dot is d little u. So rho dot minus d little u is equal to 0. The middle equation is the evolution equation. Little u dot is capital U double dot, which is d sigma, because that's d star u, plus d star rho, because that's d star du. And you notice the nice skew symmetric form of this. We have d here and the negative of its adjoint here, and d star here and the negative of its adjoint. So this being skew symmetric means we'll be easy energy estimates. If you take the inner product of this with sigma up, this term will drop out, and you'll get a conservation of the L2, sum of the L2 norm squared of the three components, which is your first stability estimate. This is a symmetric hyperbolic system. Interesting thing, symmetric hyperbolic systems lead you to skew symmetric operators. The weak form is written here. We're looking for a sigma u rho that maps 0t into the first space v0, the second space v1, and the third space w2. I don't put v2 because there's no d's on rho anywhere, so I don't need it to be in the domain of d. And I multiply by the test functions. And how do you prove this is well posed? Well, you could do it directly from the skew symmetry, or that means it's a trivial case of Hilly-Yosita's theory.
That may ask
Of course.
another time the same thing. Why are you doing this particular change of variables, or you're setting up sigma, rho, and u?
Because I like the form of this equation.
Yeah, I do like it.
So for example, I mean, it immediately tells us that the L2 norm of sigma plus the L2 norm of u squared plus the L2 norm of rho squared is constant in
Yes,
time.
I agree with that.
I'm not saying that it's the only way to do it, but it's one way to do it. It seems to me the most natural one. Now you might complain. You might say, well, the variable that you're looking for is capital U, and it doesn't even show up in the equations. Where do you get capital U? In this simple case, of course, capital U is the integral in time in little u. You can put in one more equation, capital U dot equals little u. And if you have a nonlinear problem or a problem where u enters in some other terms here, low order terms or something, then you need to do that as well.
But you like to have one instance of this d and just first derivatives in time.
Well, first of all, I definitely want for only one derivative, that is one d in space. And I like my mixed method, so there are no d stars here. There's only d's, and d star comes in weakly. And I like reducing it to first order in time, but you could argue about that. Anything else?
What are the spaces again? Sorry, I missed that.
Excuse me?
The spaces, the V0, V1, and the W, how do they compare to the Hodge complex?
So you take three of these spaces in a row from your WK minus 1, WK, WK plus 1. And you have your operators D here, DK minus 1 and DK. And V is just the subspace of this, which is the domain of D. So this, in the first space here, this space is L2 and this is H1. The second one, this is L2 vectors and this is H curl vectors. Okay? So the V just means that they're in the corresponding W, W0, W1, and W2, and also D of them is well defined. And you see we need sigma to be in D0 because we have a D sigma here. Other questions? Okay, let's take a real example. So one of the most important equations in physics. So Maxwell's equations, as it's usually written, D dot is curl H, B dot is minus curl E. We have these sort of very clean, very exact equations, and then it becomes complicated because of constitutive equations. And in the simplest case, D is some epsilon E, and somebody will remember which is permeability and which is permittivity, but it's one of those. And that could be a scalar, it could be a matrix, it could depend on X. And similarly, B is mu H, and whichever epsilon was, mu is the other one. And then we have the constraints that D is divergence free and B is divergence free. So how do we, I claim that this is really just the Hodge wave equation. So how do we turn this into the Hodge wave equation? Well, it's a little bit surprising. Of course, there's choices. You could do it in different ways. My choice is I'm going to discretize as my variables E and B. And I won't have a D or an H in it, but of course you can always get D as epsilon E, and you can always get H as mu inverse B. In addition, I'm going to throw in another variable, sigma, which is going to be a scalar variable, and that's going to actually turn out to be 0. And the purpose of sigma is there's only a solution to Maxwell's equations in the case the initial data is divergence free for D and divergence free for B. I would want to have some equations that I could solve for any initial data, because there could be some noise or something. But for good initial data, sigma will be 0. Okay, now where are my sigmas and my E's and my D's? My E is going to be a 1 form sitting in this space in the domain of the curl. My B is going to be a 2 form sitting in this space in the range of the curl. And my sigma is going to be a scalar function, which is going to turn out to be 0 in the range of the gradient. Okay, how do I handle the permittivity and permeability? Well, that turns out to be super simple. Even in the anisotropic variable coefficient case, you just use a weighted norm in your L2 spaces, weighted by epsilon or by mu inverse. So nobody said the Hilbert spaces had to be the usual L2. I'll take them to be a weighted L2. So my 3 Hilbert spaces are L2 weighted by mu inverse, L2 weighted by epsilon, and ordinary L2. I could weight that one too if I wanted. And then my Hilbert's complex has the grad and the curl in it. To agree with traditional Maxwell notation, you should take minus curl, but that doesn't matter. And then here is exactly the Hodge wave equation, exactly these equations here. And I'm just putting in for D and D star the correct curl or grad that we get. Well, we don't have any D stars, so I just have to put in for D the correct either grad or curl. So our method is to find sigma, E and B. Sigma is a scalar, E and B are vectors, functions of time, such that sigma dot tau is minus epsilon E grad tau equals 0. Well, if D turns out to be divergence free, then this term will be 0, because I can integrate by parts. And I'll get divergence E is 0, so sigma dot will be 0, and if sigma starts out 0, it'll stay 0. So this equation is basically putting in div D equals 0. This equation, epsilon E dot, this term will be no, this term won't be 0. This term, yeah, there's a sigma in there, and sigma will be 0. So this term will be turn out to be 0, and it says epsilon E dot is, well, in a weak sense, we integrate this curl by parts, and we get curl mu inverse B. So this is the equation D dot equals curl H. Mu inverse B is H. And then the last equation is the equation mu inverse B is equal to curl of E. Mu inverse B dot is equal to, sorry, mu inverse B dot is mu inverse curl E, which is the same as B dot is minus curl E, which is the other Maxwell's equations. And so this is exactly the Hodge wave equation with these weighted norms is nothing other than this formulation of Maxwell's equations. And the theorem is, if you start out with a sigma that's 0, and you start out with initial data that satisfies div epsilon E is 0 and div B is 0, then they will vanish for all t, and EB and epsilon A mu inverse B are the exact solutions of Maxwell's equations. So Maxwell's equations is the Hodge Laplacian in this sense. Any questions? So for example, we've just proven that there exists a unique solution to Maxwell's equations. We proved it's well posed up to harmonic forms, and we know what the harmonic forms are and so forth. Okay, and finally let me end this section by saying not everything is the de Rham complex. Of course, it would be extremely embarrassing if you had this beautiful theory about Hilbert complexes and there was only one example. It's not the case. But it may seem that way the first time you read through it. So this is my favorite complex. Instead of L2 scalars, we start with L2 vectors. And then the second space, instead of L2 vectors, is L2 symmetric matrices. That's what the S means. V means vectors, R3. S means 3 by 3 symmetric matrices. And the first operator is the symmetric part of the gradient. So the gradient of a vector is a matrix, and you take the symmetric part of that matrix, which of course is called the infinitesimal strain and elasticity. Or sometimes this thing is called the deformation of the displacement vector. So the first operation is symmetric gradient of the displacement vector to get a strain vector. The second operator is very different. It's a second order differential operator on our Hilbert complex. So if you thought this might be this one in disguise, it's not, because it has a second order differential operator. And what is that operator? It takes a symmetric matrix field, 3 by 3, and gives you a new symmetric matrix field by taking the curl of every row and then the curl of every column. And that gets back to symmetry. And that operator is somewhat known. In various contexts, it's called the incompatibility operator, the density of dislocations, the Airy potential, and so forth. It's used in classical elasticity. It gives you conditions for something to be a strain tensor, a symmetric gradient. That is, it's an identity that the curl T curl of a symmetric gradient is always 0. It's also called the Saint-Venant tensor. The third operator is just the divergence on a symmetric matrix field to give you a vector field. That's the way you go from a stress field to a loading vector in elasticity. So all these things have a meaning in elasticity, so we call this the elasticity complex. It's also called the Kroner complex and the Calabi complex. So it's a Hilbert complex. It's a closed Hilbert complex. Everything I said applies to it. At every level, there's a Hodge decomposition, there's a Poincare inequality, there's a Hodge Laplacian, there's harmonic forms, there's dual operators, and so forth. And all the theorems apply to it. And what do they give you? Well, we could go down it one by one for each group of 3 spaces. We could work it out. I'll just mention 2 key ones. If we start with the first 3 spaces, starting with the 0, this gives us, and then we use a weighted L2 norm, this would give us the inner product of C times the strain tensor against another strain tensor is equal to FV. I should write it down. That's the elasticity equations in their classical primal form. The inner product of some weight times symmetric gradient of an unknown U versus the symmetric gradient of an unknown V is equal to the inner product of F and V. And this would more typically be written C epsilon U in elasticity literature, epsilon V equals FV. That's the way in the first chapter of a finite element book in engineering they say how to solve the elasticity equations. If you go to the end of the complex, then you get the mixed form for the elasticity equations, and that's where this actually all began. People have been trying for decades to get good mixed methods for solving the elasticity equations, and this was a method to crack that problem. In the middle, you get very interesting things that have to do with dislocation theory and even applications to Einstein's theory of relativity that maybe I'll say something about at the end of the lectures. Okay, so here's another complex. Interestingly enough, it involves 2 first-order differential operators as differentials and 1 second-order. Here's another complex with the same qualities, but where the second-order differential operator is the Hessian, and it comes first. The Hessian maps scalars to symmetric matrices, and that can be extended to a complex by putting the curl operator here. The curl of a symmetric matrix field is always trace-free. So we have the curl from symmetric matrices to trace-free. And then you can take the divergence of the trace-free matrix field and get a vector field. That we call the Hessian complex. And that also gives rise to a whole bunch of interesting problems. In particular, if you use the first three spaces, you get a standard method for solving the biharmonic equations. And if you solve the last three equations, you get something, no, not the last three, the second three systems, you get equations that are the linearized form of the Einstein-Bianchi equations, which is one of the formulations of the Einstein equations from GR. And there are other examples along these lines. Andrea.
So you have these compatibility conditions, the curl, I mean, which is basically second derivatives are zero somehow, right? If you use them in the
Certain combination of second derivatives.
Yeah. Yeah, but so in the stress strain thing, when you use these compatibility conditions to compute the stress from the strain, then it's basically second derivatives, mixed second derivatives are zero, right?
No, it's not mixed second derivatives, more complicated than that. So even in 2 dimensions, if you take a vector field and it's a symmetric, if you take a symmetric matrix field that you get as the symmetric gradient of a vector, then that will satisfy. You take the curl of the rows, and then you take the curl of that vector that pops out. The curl of that is equal to 0. And is that if and only if?
Yes.
No. There's harmonic forms.
Yeah.
There's homology. The difference between the range of symmetric gradient and the null space of curl is exactly the homology of this complex, which has dimension in 3 dimensions 3 times the homology of the de Rham complex. Right? So all these have homology. But in the contractible case, you're right, which is what you were thinking.
So my question is, you have there the compatibility conditions in the Hilbert complex or in the elasticity complex. For these other things, for these other complexes, do you also have their compatibility equations somewhere, or do they appear?
The statement that take 2 operators in a row, you get 0, is a compatibility condition. It says to be in the range of this, you have to be in the null space of that. Every one of them is a compatibility condition. And every one of them, I can try the same trick question with Franco and say, is it if and only if? And the answer is no. The harmonic forms measure the difference. Okay, so that was the problems. And I left myself 10 minutes for discretization, but we do have 2 more lectures, so it's not so bad. I am going to get started on discretization. You're probably dying for it by now. So let me give you motivation. I probably won't get beyond motivation. Some numerical calculations of simple academic problems to show even in simple situations, if you don't use the right kind of methods, things go badly wrong. So I took a 2D example rather than 3D. Sometimes I write the complex in terms of the base spaces W, L2, L2, L2. Sometimes I actually write the domains, in this case H1, and this is the scalar curl in 2 dimensions. And with these 3 spaces, we get the 2-dimensional Hodge-Laplacian minus grad div plus curl rho u is equal to, so this looks like I'm doing the eigenvalue problem, equals lambda u. Okay, and so I want to solve this is the vector Laplacian eigenvalue problem on an annular ring. I took it a little non-symmetric to avoid multiple eigenvalues. And I want to solve it by finite elements. And remember, I have 2 weak formulations, the primal one and the mixed one. This one is to show you what can go wrong if you use the primal one. So I will use the primal one. I'll do sort of the obvious thing here. I'll say the inner product of div u with div v plus the inner product of rho u with rho v is equal to lambda uv. And I'll stick in finite elements. And here I took a mesh with 4,000 elements, and I used P1 finite elements, usually Lagrange finite elements, vector valued, of course, because u is a vector. And this is what you get with 4,000 elements. You get the first eigenvalue is 1.94, and the first eigenfunction looks like that, second, third. In fact, here's the convergence history, starting with 64 elements, 256, all the way up to 1,000,000 elements. the first eigenvalue converges quite nicely to 1.94, the second eigenvalue to 2.02, and so forth. The only problem with this situation is this is the correct answer, analytic. The first eigenvalue is 0. Of course it's 0. The first eigenvalue is whether there's a harmonic form, a hole in your domain, and I see a hole. So the first eigenvalue is precisely 0. You miss that. But the second eigenvalue is like 0.6. It's not anywhere near any of these numbers. So this method converges nicely to the totally wrong solutions. The simplest, straightforward, piecewise linear, finite element method using the primal formulation. So there's something to worry about here. Now I did the same method using the methods that are based on the mixed formulation and the appropriate choice of finite elements, some sort of Ravi-Artoma-like finite elements. And same problem, and you see you get a totally different answer. We're computing the same thing. But now you get the eigenvalue is 0. Actually, the numerical eigenvalue is 0 to 13 decimal places. Except for round-off error, it is 0, even the numerical one, no matter how many elements you use. And you see, well, there you see it. It's 0 straight across, no matter how many elements you use. So it converges to 0. But the other ones also converge. They're almost perfect with 64 elements. And by the time you get to the fourth eigenvalue, you need, 4,000 elements, and so forth. But these ones converge beautifully. So when I say you should use the mixed one, you shouldn't use the standard one. At least in this way, it's crystal clear. So, by the way, that has a lot to do with the singularity at the corners of this annulus. There's a, sorry, I'm going the wrong way. There's a sharp singularity at these corners, which you can just barely see there. It's not even in H1. It's a bad singularity, and that's what's going wrong here. Here's a problem that has no sharp corners. No singularities are involved, and it's another problem. This is the Hodge-Laplacian, not the eigenvalue, just grad div minus curl u is equal to f, and f is a linear vector field, something very simple, 0, x, I think. And this is what happens if you compute it with standard finite elements. You get this picture. And this you can think of as either one of two things. This is either the exact solution or the thing computed with mixed method. They're both about the same. You couldn't see the difference. The mixed method gives you the solution, which is nothing like this, not even in magnitude. This has a magnitude of 2 1/4. This is 0.07. This misses it completely. And what's going wrong here is the standard method doesn't capture that there are harmonic forms. It doesn't get the cohomology right. And therefore, it's dealing with a singular problem, nearly singular problem. While the mixed method puts harmonic forms in the method and captures them exactly, as we'll see, and so it doesn't have that problem. And now that one was to convince you that there's big advantages of the mixed formulation over the primal formulation. The next one is that you have to choose the finite elements right for the mixed formulation. And that'll be a big part of our future efforts. So here I took the problem of Darcy flow. V is minus k over mu grad p, div v is f, which is just Laplace's equation, div k over mu grad p equals f, written in a mixed form. And I took some mesh and I solved it in the mixed form using for the scalar variable p, piecewise constants, and for the vector variable v, piecewise linear vector fields. And there's my mesh, and this is my picture, and that may be pretty, but it's not right because this jumping of colors means it's oscillating like crazy. And here's the solution along the diagonal, and indeed this piecewise constant is oscillating like crazy. Now I change the elements to use the Ravi-Artoma mixed methods, mixed elements for the velocity and still piecewise constant for u, and then you get a piecewise constant solution, which looks pretty smooth and pretty decent. Of course, it's still piecewise constant. And then I use mixed elements of higher degree, the next higher degree, and then you get a nice smooth curve. So this is just demonstrating to you when you use mixed methods, you have to choose finite elements which are stable for those mixed methods, and it makes a big difference. And then this is a real problem, and it even has a movie which I won't show, but let me just give you the numbers just to show that the real problems can be done. This was done by the group of Dan White at Los Alamos. They're solving the time-dependent Maxwell's equations using essentially the method that I wrote down and using the right kind of mixed methods. And they were investigating the following question. You have a building, and it may or may not have reinforced concrete. There may or may not be metal bars in the concrete. And the question is, does that affect what you see if you look at it with electromagnetic radiation? So you send in a Gaussian pulse, and it scatters back. And how does the presence of the rebar, the reinforcement, affect the scattering? And so you need a very fine mesh, because this is on centimeter level. And so they use 10 billion brick elements with 1 centimeter resolution, leading to a system of 60 billion unknowns, 12,000 time steps, and they get a very pretty movie out of it. This would be totally undoable with the primal methods, or without good choice of mixed finite element methods. Okay, so I think that's where I will stop, and then next time we'll pick up with how do we get these discretizations, and the theory will take 2 steps. One, we'll think in the abstract Hilbert complex system. If we have a Hilbert complex, how do we discretize its Hodge-Laplacian? We'll get certain hypotheses that have to be satisfied, and then we'll take the case of de Rham and see how we satisfy these. That'll lead to the elements like these Raviart-Thoma elements and the other ones for all these other problems. And then with the last talk that I won't have time to get to, we'll talk about other complexes. Thank you.